So today we are going to talk about the cheapest link algorithm. This is our fourth and final algorithm for traveling salesman problems, which is Hamiltonian graph theory. The cheapest link algorithm is fairly similar to nearest neighbor, except in the way that we approach it overall. What I mean by that is we worry even less about um, the starting and ending point with this algorithm than we did with repetitive nearest neighbor. Okay, so we're going to write out the steps first, and then after we write out the steps, we'll do a couple of examples of the cheapest link algorithm with complete graphs with I think we've got a K5 and a K7 weighted graph for us to look at. So here's how this works. Okay, the cheapest link algorithm is a four-step process, although one of those steps gets repeated sometimes a lot of times. The first step is we look at the graph and we choose the cheapest edge in the entire graph. It does not matter what two vertices that edge is connecting. We're simply going to pick the cheapest edge, period. Okay, we're going to look at the graph, we're going to find the lowest number, we're going to highlight that edge because that edge is going to be part of our Hamilton circuit. Okay, ignore the starting point, don't worry about the starting point, you're looking at the whole graph, picking the cheapest edge. We'll then basically we'll repeat that step because the second step is to choose the next cheapest edge in the entire graph. So our first two steps involve picking the two cheapest edges in the entire graph. Don't worry about where it starts, don't worry about where it ends. Just look at the graph and highlight the two cheapest edges in the entire graph, period. Okay? Now once we've done that, we're going to continue to choose the cheapest edge but we have some rules. Okay, the first thing we cannot let happen is we cannot let any circuit form. Okay, it doesn't matter how long the circuit is, we cannot have any circuits until we are done. We don't want any circuits, okay? And the other thing we cannot do is we cannot choose, or we cannot allow more than two edges to be selected from a single vertex. Because once we've selected two edges from a single vertex, we have visited that vertex and left that vertex. We don't need any more edges from that point, okay? So those are the two things that are going to continue to happen. Once we have all the vertices are joined, we will then close the circuit and find the weight. Now it's worth noting that this is where we care about the starting and end point. While we're doing the actual algorithm, we do not care at all what the problem says to do in terms of starting and ending, okay? We are just literally going to go in here and we're going to pick the cheapest edge over and over and over again, except we are not going to allow any circuits to form, okay? And we are not going to allow more than two edges to be picked from any vertex, okay? So those are going to be our steps. If you want to grab a screenshot, grab it now. We're going to be continuing into the examples next. I really feel like as decent as this is to explain in words, it is much easier to see done in practice. It is probably the easiest algorithm we've done, in my opinion. So we're going to go through a couple of examples. Here we go. So we're asked to run the cheapest link algorithm to find a circuit from vertex D. And again, we don't really care about where we are starting this vertex from, because when we run the cheapest link algorithm, we ignore the starting point, okay? So we're going to start by choosing the cheapest edge. So we take a look at this graph and we look for the lowest number in the entire graph. The lowest number in the entire graph is 119 from A to C. Okay, so that is the cheapest edge in the entire graph. So pick that one. Then we choose the second cheapest. So we look again and we look for the second cheapest edge in the entire graph, which is 120. Okay, so we would pick, what happened? Back over to that. There we go. We would pick CE for our second edge. Okay, and again, we're not worried about, and it didn't come back. Great, lovely. Hold on. There we go. It doesn't matter where we start. Okay, what we're interested in is picking the cheapest edges we can possibly pick, in hopes that we will find the cheapest Hamilton circuit that we can possibly get picked out. Okay, so once we got our two first edges picked, this is the first place where we might have to eliminate some stuff. Okay, what I mean by that is we have rules. We can't allow any circuits to form, which means AE cannot be selected, because if we picked AE, that would close that circuit ACE. So just go in and cross out AE's weight so that you don't accidentally pick it again later. Okay. We're also going to be eliminating BC and DC, because we already have two edges at vertex C. So we're not going to be selecting those, because that would give us more than two vertices picked at C. So we go through our steps. We say, okay, are there any that would cause a circuit to form? Yes, those get eliminated. We already picked two edges from a single vertex? Yes, the rest of the edges at that vertex get eliminated. So AE, BC, and CD are not going to be selected for our answer, period. So we cross them out so that we cannot make that mistake. Then we pick our next cheapest edge, which would be, looking at our options there, we got 150, 152, 199, 185, and 200. So we would pick the 150 because that is the next cheapest edge. That'd be BD. Okay. Now, BD is not connected to the other piece, the ACE piece. So no edges are going to be eliminated. Okay, we don't have anywhere where a circuit can form, and we don't have any spot where we've picked more than two edges. So we're just going to go back and we're going to say, okay, what is the next cheapest edge? Well, the next cheapest edge would be AD for 152. Okay, so at this point, there's a whole bunch of eliminations that happen, okay? AB gets eliminated. because we've already got two edges at A. So they don't need that number. And DE gets eliminated for the same reason. We already have two edges at D. Now, if you notice, all vertices are now connected. Which means now we're going to go and we're going to close the circuit. Okay? So we go in here and we choose the edge that would close the circuit. Well, that would be BE. So when we select BE, that closes our circuit. Okay? Our circuit needs to be written so that it starts according to the directions at vertex D. Okay? So this is where we care about the start. Because when we write our answer, we're going to write our answer starting at vertex D. And it doesn't matter which direction we go, we're just going to follow that highlight. So our answer is going to be, say, D, A, C, E, B, D, which if we trace that, that's what we're doing here. We're going from D to A to C to E to B and then back to D. That's the Hamilton circuit. Okay? Then we need to add up those weights. So DA is 152, AC is 119, CE is 120, EB is 200, and BD is 150. Add all those up, and we get a weight of 741. So our answer would be the circuit DAC EBD with a weight of 741. I do think this is the easiest one once you get the hang of it. I think it's significantly easier than brute force or repetitive nearest neighbor. It may not be easier than nearest neighbor. That one's not very hard either. Okay, but I do think that this is one of the easier algorithms for this process once you get the hang of it. Now, again, this is the first example, so it's going to seem a bit, I'm writing a lot of work out there. You don't have to show all of that work, okay? You can just go through and say, choose AC, choose CE, and then you can write eliminate AE, BC, DC, and then you can write choose BD. That's how you show your work. You just state what order you're doing stuff in, okay? You don't have to write out all of this for your work. Then at the end, I do want to see the work where you add up the circuit. So I want to see the 5 numbers that you're adding together along with your answer written as if it started at point D. Now, the major mistake that people make when they do this algorithm, the one that happens by far the most often, is that they think that like repetitive or like nearest neighbor and repetitive nearest neighbor, that they have to care about the starting and ending point, D. We don't care about where it starts and ends until we are writing our answer at the very, very end, okay? So we're just going to go in and pick the cheapest edges in the entire graph, period. And as we do that, anytime we have an edge that would close a circuit, we eliminate it. Anytime we have already picked 2 edges from a vertex, we eliminate the rest of the edges from that vertex. So the longer the process goes, the easier it gets to pick out the cheapest edge. Okay, so there's the full first example written up on the screen with all of the work. You may want to grab a screenshot of that. We're going to go do another example, and then we will be moving on to the assignment. We'll be done for the day, okay? So 5 to 7 more minutes here, and we will be done. Everybody hopefully has grabbed the screenshot if they want one. We are going to move on to the other example. This one is a bigger example. I wanted to show you that the process doesn't really get any more difficult no matter how big the graph gets. It is a K7 big guy. Okay. Okay. Yeah, you don't need to be able to draw it necessarily. Although I suppose e-learning wise, it probably would be easier to have it drawn. If you search on the internet K7 and have a printer, then you can get a picture, and then you just have to label it. So there's a lot going on in this picture, but the process doesn't change. Okay. We're going to start by choosing the cheapest edge. So take a minute, look at that picture, and find the cheapest edge in the entire graph. Okay. I am seeing that the cheapest edge in the entire graph is DE. Yep. There you go. Okay. Then we pick the next cheapest edge. Well, that one's not much harder to find. There's only one other one that is less than 2,000. That is EF. So that would be the one we would pick next. So we would eliminate DF because it closes a circuit. And we would eliminate all of the other edges from point E, which would be E to C, E to B, E to A, and E to G. Again, our reasoning there is that we already have two edges that start at E. So we would go in and we would cross out the 2,200 from D to F, the 3,500 from C to E, the 6,000 from B to E, the 3,000 from A to E, and the 4,000 from G to E. We're now ready to choose again, so we're going to choose the next cheapest edge. So again, take a minute, take your time, make sure you pick the correct next cheapest edge, which would be A to G for 2,000. Now that is not connected, okay? Since that is not connected to the DEF piece, there will be no eliminations. We just go on and we pick the next cheapest edge, okay? So again, we take our time, we look at the graph. Looks to me like we have two edges tied for the next cheapest. And since neither one of them would create a problem if we would select them, we have a tie. So we would pick both AF and CD. Okay, now this is going to create a lot of eliminations, okay? Because once we've picked those, we have our two edges at D, so that would eliminate three more numbers, okay? It would eliminate the 3,200 from D to G. It would eliminate the 2,900 from D to A, and it would eliminate the 5,000 from D to B. Same thing at A. We already have two edges from A. So we would also eliminate AC and AB, the 4,000 and the 6,000, because we have two edges at A. We would also eliminate the other two edges from F, which are GF and FB, because we have two edges at F now. So the 3,500 and the 7,500, oh, I missed one, and FC, the 5,000, because we already have two edges at F. Okay? So, and I noticed some of us are having some connection issues today. Don't worry, this is being recorded. The video will go up in recording form as soon as I get it up. Okay? That doesn't leave very many options left to pick from in terms of closing this thing. And actually, there's one more elimination because it would close the circuit too early. CG is also going to be eliminated. Because if I were to pick that, I wouldn't have visited B. Okay? So if you look, there aren't many edges left to choose from here. Okay? In fact, we only have two edges left. Okay? So our fifth choice, our next choose next cheapest, would be BC for that 3,000. And then all of the points are connected. So we were now going to close the circuit. Okay? So our final step here is going to be to close the circuit by choosing the last edge, BG. So there we have our circuit. Now we were told to write it as if it started at vertex A. Okay? So our answer would be A, and then we just go follow the highlighted path. It doesn't matter which one. BC, no it does not. It does not break a rule because it only had one edge at C. We start at A and we follow our path. A, F, E, D, C, B, G, A. And then we need to add up those weights. That'd be 2,800 plus 1,500 plus 1,300 plus 2,800 plus 3,000 plus 8,000 plus 2,000. So our final answer, we would add those up. And we would end up with a weight of 21,400. Okay. So there are our examples. I'm going to stop the video. If anybody has any questions, please send them in the chat now.